Okay, so I think we can start. It is 2 o'clock sharp. We are in Trieste at the University of Trieste in the Department of Mathematics and Geosciences. And we have the honor of having a guest lecture today by Professor Yuri Fialko. And Professor Yuri Fialko has been invited through the Department of Excellence, which we have at our department, to stay for several weeks now for a cooperation on crustal deformation. So our mutual interest in this respect is to use the differential InSAR, so interferometric radar acquisitions from satellite, for instance, the ESA satellite Sentinel-1, to obtain crustal deformation in Italy or other areas of interest. And since Yuri Fialko is expert on this subject, both in data acquisition, usage of the software which has been developed at the University of San Diego, and also the interpretation of the data, we have been discussing these subjects over the 3 weeks. So Professor Yuri Fialko is expert in space geodesy, crustal deformation, earthquake physics, and active volcanism. And okay, so yours is the floor for 1 hour.
I'd like to apologize. I've got a bit of a cold, so I know I'm going to sound terrible, and I'm really hoping that my voice does not fail me, but we'll see how far we can go. So today I'd like to talk to you about an old problem that started with observations made about 50 years ago. At that time, these observations did not have a good explanation and were sort of filed away as a curiosity that doesn't make much sense. And then the problem resurfaced again recently as new observations became available. So the problem that I will be talking about is concerned with unsteady creep, also known as slow slip events or episodic slip events on major crustal faults. And for this talk, I will be focusing on the San Andreas Fault in Southern California. So this picture on the background shows how slow slip looks like to geologists who go out in the field and happen to be at the right place at the right time. So I will come back to these field observations later. And before I begin, I'd like to acknowledge people, my collaborators, who contributed to the results that I will be presenting today. So here's an outline of my talk. I will start with some background on the San Andreas Fault, focusing on its southern section, as I will demonstrate to you, host a whole spectrum of different behaviors, whole spectrum of different slip modes. And I will cover some theory of time-dependent creep, present new observations of a significant slow slip event that started on the Southern San Andreas about 2 years ago and may still be ongoing. And I will try to convince you that this slow slip event was triggered by an earthquake that occurred several thousand kilometers away. And then I will present results of numerical models that help us link the observations to fault zone properties and understanding of the long-term fault operation. So I appreciate that in this audience there may be people with very different backgrounds, and I will try to avoid jargon as much as possible, but if there are any questions, I encourage you to stop me and ask at any point. So as I'm sure many of you know, San Andreas is part of the plate boundary between the North American and Pacific plates. It's a strike slip fault that accommodates on average between 30 to 35 millimeters per year. It's a fault that is capable of great up to magnitude 8 earthquakes. I think it's fair to say that San Andreas was the birthplace of modern earthquake seismology, which really started after the 1906 San Francisco earthquake that produced not only extensive damage, but also it enabled a collection of very important scientific data that really shaped how people think about the causes of earthquakes and how earthquakes occur and why do they occur. And one of such data sets were geodetic observations of displacements at the Earth's surface made as a function of distance away from the fault, as shown here. These observations became a basis, a part of so-called elastic rebound theory and the subsequent theories of the earthquake cycle. according to which slip on the fault that occurs during earthquakes and may last for seconds to minutes results from stress accumulation in the interseismic period on a fault that is being locked by friction. So at greater depths where temperatures are high enough and pressures are high enough, rocks are able to creep at more or less constant rate as dictated by plate motion. But here in the upper section, because the fault is locked, it's accumulating stress in the interseismic period. And eventually when that stress becomes large enough, the fault fails and releases stress. And over multiple earthquake cycles, they combine displacements from the co-seismic and the interseismic deformation, sum up to what we can easily understand as the block motion that represents the motion of tectonic plates. So the process is somewhat more complicated in that mature long crustal faults like San Andreas do not rupture at once in one single event, luckily for us, but they tend to rupture these segments of the fault such that stress is being transferred from one segment to the other, and then the process continues. So this is well illustrated by a history of earthquakes that we have from the written records in California on the San Andreas Fault. You have to realize that unlike in Italy, written records in North America do not extend very far back in time. So here the timing and the spatial extent of significant earthquakes is shown by color. So starting in 19th century, the central section of San Andreas was ruptured in the Great Fort Tejon earthquake of 1857. Luckily at that time, not too many people lived in this part of California. Then in 1906, the Great San Francisco earthquake ruptured the northern section of San Andreas. The central and northern section of San Andreas are separated by what we call the creeping section, in which the two sides of the fault are just happily slipping past each other, so there is no elastic stress accumulation, and therefore this section does not really have a potential for producing significant seismicity.
Is it unexpected that the 1812 would re-rupture in 1857, only a short time later?
It's not really unexpected in that, as you know, earthquakes are not a particularly periodic process. So the recurrence interval in any particular part of the fault may vary quite substantially. So this is perhaps a shorter recurrence interval compared to the average, but it's not completely out of ordinary. But that's actually a good point. In the last 50 years, we had some significant activity in the southern part of the state, where these blue lines show magnitude 7 earthquakes. And you can see that we had, most of them actually happened around Southern California. But you may also notice that the southern section of San Andreas Fault remained quiet throughout that time. And so this created a question, basically, why is this part of San Andreas not producing large earthquakes in historic times, basically in the last 300 years for which we have written records. This, combined with some early observations of surface cracking on the fault trace that geologists were able to document, have led some famous geophysicists to suggest that the southern portion of San Andreas may be creeping. It's basically unlocked, freely sliding, pretty much similar to the behavior of the central creeping section of San Andreas. That, of course, would have been a great news for 25 million people who are now living in Southern California, in particular for those in the Los Angeles and San Diego metropolitan areas. But when geologists went out and started digging trenches across the fault, they found evidence for past earthquakes. So here the dots show the geological excavations, and you can see that on Southern San Andreas there are several places that show that the fault was seismic in the past. And in earthquake geology, the past is the key to the future. If the fault is able to produce an earthquake at some point in the past, it will do so again at some point in the future. So these different views perhaps can be reconciled by assuming that the fault may be locked at some deeper portion in the seismogenic zone, but that it may be unlocked at some shallow depth interval. So it may be creeping at the top and storing elastic energy at greater depths. This hypothesis, these possibilities can be tested with precise geodetic measurements of surface displacements or surface velocities, such that the three scenarios that I've been mentioning would be the fault that is completely unlocked all the way from the top to the bottom, in which case this will be the displacement profile. It's essentially a step function. And this would be this classical sigmoidal profile that is expected of a fault that is locked at the surface throughout the seismogenic zone and then is slipping below the seismogenic zone. And this will be basically some combination of the two. This is the fault that is locked at some depth interval, but it's unlocked very near the surface, so it's able to creep and release stresses in that shallow interval. By now, I think geodetic data are fairly convincing that it's this third scenario that is most consistent with observations. This is a velocity profile across the Southern San Andreas Fault, which shows that there is this curvature in the velocity profile, which means that there is elastic stress accumulation. There is very clear evidence from the data, but there is also a bit of a discontinuity across the surface trace of the fault, which means that it is indeed creeping in the shallow portion of the fault. These measurements allow us to estimate the so-called slip rate, the long-term slip rate at which the fault is moving at depth. So we call this the geodetic slip rate, which turns out to be on the order of 15 to 20 millimeters per year. If you take that number and multiply it by the seismic quiescence, the time for which we did not have a large earthquake, 300 years, we end up with a slip deficit of 4 to 6 meters. So that's the slip that will have to be released in future events. It will have to be released in future earthquakes. This is a factor of 2 to 3 larger than the average slip on that portion of the fault suggested by geologic studies. So for this reason, Southern San Andreas is being referred to as being 10 months pregnant. Indeed, it has the highest probability of a significant event over the next 30 years, as estimated by the United States Geological Survey. So just to recap what observations are telling us, in Southern California we have a strike-slip fault, which is loaded by constant plate motion at depth. It's unlocked and it's creeping at the surface. And that's kind of a behavior which is very much in agreement with predictions of rate and state friction models that postulate, in the context of these models, the creep results from the velocity strengthening conditions in the top layer of the fault. So we'll come back to that in a second and just mention this diagram, which is the prediction of these models of rate-state friction, in which parts of the, here we have depths, and this is amount of slip, and portions of the fault that are painted as blue are just sliding slowly in between the earthquakes. The portion that is painted in red is slipping during earthquakes. This is fast co-seismic slip. And the rest is taken up by the transient slip that we refer to as after slip. So now we're going to switch gears a little bit and talk about friction. And I'm just going to start by reminding everyone that to the first order, friction is characterized by direct proportionality between normal stress or normal force that is applied across the interface and the shear force that is required to initiate slip on this interface or sustain slip on the interface that is already sliding. So this is represented by this formula known as Amundsen's law. Here the coefficient of proportionality is known as the coefficient of friction, and for typical rock types it's somewhere between 0.5 to 0.8, rather constant number. Turns out that Amundsen's law was in fact already known to one great Italian, whom you may recognize here. And this knowledge was later forgotten for 200 years, and so this relationship was then rediscovered by Amundsen and later confirmed by Coulomb, and so now it carries their names. If this law were exact, if this was the whole story, earthquakes would not ever exist. They would not happen because there is really nothing here that would allow for slip to be unstable. So this is just the statement of a force balance. Whenever you reach that force balance, you initiate sliding, and there is no recipe for instability. By the 1980s, it was established that dependence on normal stress is not the whole story. The frictional response of any frictional interface also depends on the instantaneous sliding velocity, but also on the slip history. So this is encapsulated in the so-called rate and state equation that was originally proposed by Dietrich and Reina in the early 80s. And what this relationship is saying is that it starts with the classic Hamilton-Coulomb-Da Vinci law and adds two terms to this law. So there is one term that depends on the velocity or the logarithm of velocity, and there is another term that depends on the slip history throughout this state variable. So since I'm in the Department of Mathematics and Earth Sciences, I thought that I'm allowed to show equations, and there will not be too many equations here. The evolution of state is described by an additional equation, which is known as the evolution law, of which several types were proposed. The most popular, the most commonly used ones are the so-called aging law and slip law. At steady state, that is when the state does not change over time, so the derivative is 0, the evolution law drops out, and we have the dependence of the steady state coefficient of friction only on velocity. Most importantly, the sign of this parameter a minus b, and a minus b are just these coefficients in front of these two terms that may depend on the material properties. For example, the rock type, they may depend on ambient conditions such as temperature, but otherwise they are considered to be material properties. So the sign of the a minus b in fact determines the response of this frictional interface, such that if a minus b, this parameter, the difference between the two numbers, is positive, we call this velocity strengthening friction, because any time when the slip on the interface speeds up a little bit, so the interface starts to slip faster, it means that resistance is going up. And so this is a recipe for stable slip, because this is a self-arresting mechanism. Whenever you accelerate a little bit, there is greater resistance, and so it returns to the original velocity. On the other hand, if the sign of the a minus b is negative, so friction goes down with an accelerated slip rate, we call this behavior velocity weakening, because every time you have a bit of an acceleration, say from some spontaneous effect, the resistance goes down, which means more energy is available to drive slip, and so it just continues and it goes into instability. So this type of a behavior is conducive to earthquakes. This type of a behavior is conducive to stable sliding. So in principle, if we were able to determine the sign of this parameter a minus b somewhere in the crust or everywhere in the crust, we would be able to tell whether this particular portion of the crust is able to produce earthquakes or it will be sliding aseismically. This formulation was incorporated in numerical models that were quite successful at predicting a number of observed features. In these models, typically, it's assumed that the seismogenic zone, the zone that is able to host slip instabilities and allow slip to grow into large elastodynamic slip events, this area is bounded by the velocity strengthening layers, both at the bottom and at the top, where instabilities will be suppressed, and so the creep in those areas would be stable. This is an example of a type of a simulation that sort of starts with these assumptions, and indeed these kinds of models are able to explain or predict a number of observables. They generate spontaneous slip events. They are showing that some portions of the fault will be producing transient creep, for example, the post-seismic transients. And they explain how this transition from the aseismic to seismic portion is occurring as a function of depths. However, one thing that these kinds of models universally do not predict is any type of variability in time of the surface creep rate. In other words, these models predict that slip at the surface should be more or less constant rate throughout much of the interseismic period. And that's just simply a consequence of the fact that velocity strengthening friction results in stable slip for constant loading rate. So as I mentioned in the beginning, things seem to be a bit more complicated on real faults. It was noted as early as 1960s that on some portions of San Andreas, This is the southern portion of San Andreas, and this is a location near the transition from the central section to the creeping section. Even though, and these are, by the way, measurements from the so-called creep meter instruments that are just a piece of wire anchored on both sides of the fault, and whenever fault moves, the wire extends, and so it's able to record the amount of slip. And these measurements show that even though there is a very well-defined long-term creep rate, long-term surface slip rate across the fault trace, in reality, most of the time, the fault spans at the velocity which is much smaller than the long-term average. And then occasionally it would accelerate in these small slip events and then kind of return back to the slow state. So same behavior was observed also around Parkfield. And one thing that was really surprising about these observations is that this kind of unstable sliding associated with the fault that is nominally creeping was not observed in the laboratory experiments. It was noted in papers that described this phenomenon. So 40 years later, we know that it's in fact possible to produce unstable slow slip in the laboratory. This is an example from the direct shear experiments in which we have a transition from stable sliding here. This diagram shows displacement, so measured displacement of a block sliding on top of the other block as a function of time. When this is close to the straight line, it's just following the driving velocity. Then it transitions to these periodic, semi-periodic slow slip events, and eventually transitions to stick slip, which is the laboratory analog of earthquakes. And the only thing that is changing in these experiments is temperature. Just by changing temperature, not everything else being the same, we can affect these transitions in the slip stability from stable slip to unstable slip with intermediate slow slip conditions. So that's the kind of a behavior that we would expect to be consistent with what our observations are telling us, and that's the hypothesis, the fact that it's the rate and state friction effects that are causing these slow slip events that I will explore a little bit further later in this talk. So many of you may have heard about slow slip events that are happening at the bottom of subduction zones. These were a subject of much excitement and research in the last 20 years since they were discovered. And creep on shallow section of strike slip faults is very much similar phenomena, except that it's much more accessible to observations. You can actually walk to the place that is producing this behavior, and therefore it's a bit surprising to me that this phenomena did not receive much of attention in recent years. However, we have now increasing volume of observations suggesting that this behavior may be quite common and ubiquitous. These are two examples from faults. This one is in Southern California. This is in Turkey on the North Anatolian Fault. And these diagrams show the distribution of shallow creep during one of the slip events, and this is the time dependence. So for the Superstition Hills Fault here, this is the time dependence of a slow slip event, and this is a sequence of slow slip events determined for the Izmit Passes segment on the North Anatolian Fault. This data set from the Superstition Hills Fault, I think, was the first one for which high quality data were available, so I will quickly walk you through the observations. The Superstition Hills Fault is the fault just 20 kilometers to the west from Southern San Andreas. It connects to the southern termination of the San Jacinto Fault further to the northwest and to the Imperial Fault further to the southeast. It hosted a magnitude 6.6 earthquake some 30 years ago. And one interesting feature of this earthquake was that it produced no surface slip. So seismometers recorded a strong earthquake at depth, but then there was nothing at the surface. And then in weeks and months following this event, slip at the surface started to catch up with what happened at depths during that seismic event. So this is a summary of what was observed in Superstition Hills. This is a distribution of the co-seismic slip. This is an inversion based on seismic data. This is depth. This is distance along the fault. And you can see there was really nothing in the upper 5 kilometers or so. However, shortly after the earthquake, measurements made at the surface indicated that slip started to pick up, and it became larger and larger and larger with the time dependence that was roughly logarithmic in time. So this is time, this is amount of slip at the surface. So it turns out that this very similar kind of behavior was also observed in several earthquakes that happened before the Superstition Hills. And this was taken as strong evidence in support of the velocity strengthening layer at the top. So data from different places showed consistent behavior, and that's always, it's always intriguing.
But the black dots were aftershocks.
Black dots are aftershocks. I would not trust the aftershock locations. This is
if it's a layer that should resist the slip.
Yeah, no, this is a good point. I would just want to emphasize that the seismic network there was not very dense. Walter perhaps can say more about the deployment of seismic instruments. And the accuracy of these aftershock locations are at best maybe 2-3 kilometers, so you can just move around them without violating the fit to the data. But it's a good point because you can see that these aftershocks are kind of happening on the boundaries of the co-seismic slip area. And that's actually the feature that we're seeing with modern data sets that really have high resolution and high precision. And that makes a lot of sense physically because this is where you have the highest stress concentration. So the stress was dropped in the middle of this co-seismic asperity, and then it was transferred to the areas that did not slip, and this is where you expect to see a lot of aftershock activity.
So on the post-seismic slip, there's some dip right at 12 kilometers. What is that?
This one?
Yeah.
Yeah, it does look like, well, it may be a sampling problem because there may not be too many points around here in this area. So maybe just interpolation, but it's also possible that there could be two segments that are separated by some gap in the middle. Now, this is the time history of surface displacements measured by a creep meter installed across the Superstition Hills fault. In years after the earthquake, the creep rate has returned to almost a constant value on the order of a millimeter per year or so. And then in 2006, there was a large spontaneous low slip event that had a magnitude of about 3 centimeters that itself consisted of multiple sub-events. That was quite unusual, so I don't think we've seen this kind of behavior before. So a number of teams from UCSD went out in the field and found a crack that was basically a fault trace, and this crack would be followed by multiple kilometers. It was very localized, and subsequently when we combine analysis from InSAR data, and I will explain how this works in just a few minutes, with field observations that were just measuring the offset features along this crack. Right? So you can find things like little pull-apart basins, and then you can measure how much of opening resulted from this motion. And we also had 1-point measurement from the creep meter. And so these different data sets are shown here in the same diagram. This is distance along the fault. This is how much slip has happened say in 1 month following this event. The red dot is the creep meter data, the green line is the field measurements, and the blue line is the measurement from the InSAR. And so all of them are in good agreement, which means that all of that displacement has happened on this extremely localized crack interface. So it was not distributed over some broad zone, it happened on this almost razor-sharp interface like this one. And we know that because since these amplitudes are the same in something that is as localized as millimeters on the field scale, as well as the space geodetic data that sample much broader areas away from the fault on scales of tens of meters and hundreds of meters, it means that this was it. This was all of the displacement that has happened.
But this is in soft sediments, or I mean,
it
looks like dirt. So how is it so localized then?
It is dirt, and it is surprising why is it localized in dirt, but that's what the data are telling you. So yes, we would expect this perhaps to be a little bit more distributed, especially if we consider this layer to be velocity strengthening, since it's able to creep, right? Velocity strengthening usually results in strain delocalization, but yet it is highly localized here. So now going back to San Andreas, I already mentioned the creep meters measurements that showed very similar behavior there. We also have a number of other indicators, both from the geologic markers and also anthropogenic markers like the built canals. So at some point, let's say in 1945, a canal was built to carry water from point A to point B. And then later on, geologists went out and found that this canal is offset by a certain amount, by a measurable amount. And since you know the date the canal was constructed, and you know that it was straight at the time when it was constructed, there was no really reason for make it kinked or step-like. This amount of displacement that has happened since can be divided by the time, and you get an average estimate of an average slip rate. So it turns out to be on the order of several millimeters per year, similar to the measurements from the creep meters. My favorite offset feature is the Indian stone ring that you can see here. I have a little animation showing how this offset has happened. Later, we have confirmed that in fact the trace of San Andreas goes right in the middle of this stone ring. And we do not know when the stone ring was constructed, but if one assumes that whoever put it there put it right after the last earthquake that happened around 1700, the amount of offset on the stone ring roughly matches up with what we infer from other data. A few years ago, former student Eric Lindsay also did analysis of Envisat InSAR data, and this is the distribution of the creep rate along the fault, which agrees fairly well with the older measurements, data from creep meters, as well as the newer creep meter measurements that are shown here by the black dots. The only place where we have a disagreement between the InSAR data and the creep meter data is at this location called the North Shore. So this is the location of the North Shore, and that color figure here shows the horizontal displacements derived from InSAR data, and you can see that interestingly, so first of all, you can see the color contrast across the fault trace. Whenever you have the color contrast in a displacement map, it means that you have a displacement discontinuity. So this side of the fault moves this way, this side of the fault moves that way, and we can measure exactly how much slip is happening across this interface. But you can also see that in some places this surface slip, is highly localized, for example, like here in Dermot Hill and also in Mecca Hills. And in some other places like North Shore, it is more distributed. So it's happening not on the extremely narrow crack, but it's happening on the shear zone that has a width of maybe 1.5 to 2 kilometers. This is the reason for why we have a disagreement between the creep meter and the InSAR data, because the InSAR measurement are computing what is happening in the far field, and the creep meter is sitting here measuring something with a really small aperture. So creep meter is measuring 0 slip rate, and InSAR data is measuring some finite slip rate. So in terms of slip rate, there's pretty much the same amount of motion in this distributed zone compared to a localized zone. Marine geologists would immediately recognize a similarity between what is happening there on the San Andreas with what is happening on a much broader scale on the Pacific seafloor. These are major fracture zones that extends thousands of kilometers across the Pacific, and we know that this behavior is controlled by the stress conditions. Basically, whenever we have fracture zones that are under transpression, so there's extra compression acting across the fracture zone, they happen to be very localized and structurally simple. Whenever we have fracture zones that are under transtension, so there is a bit of an extensional component acting across the fault, they tend to be messy and more geometrically complex. And it's the same situation across on the San Andreas. You can see that the fault is not exactly straight, so it has these undulations, and whenever it rotates, it strikes a little bit more to the west. So if you imagine there is a long-term slip along this curved interface, so this will put it under greater compression, and this is where we observe slip to be highly localized. In these areas that strike a little bit more to the east, we have a bit of an extensional stress component, and these tend to be more diffuse. So this kind of a behavior is observed both in the Sentinel data and also in the older ERS data. We see this type of distributed deformation not only on Southern San Andreas, but also on other faults. This is an example just 40 kilometers from the San Andreas. This is San Jacinto Fault around Anza. If we take a profile across the fault and just combine all the space geodetic data that include InSAR, GPS, and other data sets, this profile is shown here. And if we zoom in on the area just next to the fault, you can see that there is enhanced strain rate. So basically the slope of this curve, which is the strain rate, is greater in the zone near the fault compared to the zone just outside of the fault. In part of this strain localization, maybe due to the fact that San Jacinto Fault is associated with a large damage zone. This color image here is the rigidity, elastic rigidity, so variations in elastic shear modulus derived from seismic tomography. So data from seismic instruments, travel times that were used to infer how fast the seismic waves are traveling through this volume. And you can see that there is a zone of significantly reduced shear modulus right around the fault trace. And this damage zone probably results from the fact that there have been many generations of earthquakes on this fault. They have produced lots of cracking. They have just completely damaged the volume of rock around them. And so now it's expressed in this effectively reduced elastic modulus. This elastic heterogeneity would enhance the strain rate. And you can imagine what happens if you shear something that has a soft layer in the middle. The soft layer would tend to enhance the deformation. It would tend to capture more of displacements in it. But it's able to this particular structure is able to increase the local strain rate by about 40 to 50%. Turns out that this is not enough to explain the observed signal. So unless the variations or the reductions in the elastic moduli are much greater than suggested by seismic tomography, the other explanation is that this additional deformation may result from inelastic yielding, so failure of the fault zone material in the interseismic period. So you can think of this as analog of shallow creep, just happening in the volume instead of on a plane. Now, we do not know whether a similar low rigidity zone exists, damage zone exists on the Southern San Andreas. In fact, we have a project right now focused on answering this same exact question. But we do know that this signal that we're measuring cannot be entirely due to the presence of the soft damage zone. And we know that because the width of this shear zone changes over time. So recently we in fact observed that with newer Sentinel data, in that in recent years the width of the shear zone has decreased quite significantly, over almost by an order of magnitude. And so this is kind of an effect that cannot result from a permanent elastic structure. This is indicative of spontaneous localization of inelastic deformation within the damage zone. So I don't think this behavior has been observed before, and we're working on understanding how this can happen. We also observe variability in deformation not only as a function of spatial coordinates, but also as a function of time. This is perhaps best illustrated by records from creep meters. These are instruments operated by Roger Billum of Colorado University. And these different color curves here correspond to records from each individual creep meter. And you can see that between 2004 and 2010, these creep meters were sort of just dragging almost at the constant rate. And then in 2010, there was a large earthquake, magnitude 7 El Mayor Cucapa earthquake that produced significant triggered slip on all of these creep meters. And then after that, they almost stopped. Actually, some of them seem to go backwards. Unfortunately, for this time period, and from 2010 to 2015, we did not have the InSAR data available due to the failure of various satellite missions. But starting in the late 2014, we had a pretty healthy stream of data coming in, and so we are able to actually compare what is happening, try to understand this temporal evolution. So since the results I will be showing you next come from this technique called interferometric synthetic aperture radar. Just want to make sure that everyone understands what this technique involves.
In the previous slide, they track each other, all except for the last event, where the blue is the only one that...
This one?
Yeah.
Yeah, and that, well, there is a bit of action going on, but what it means is that the slip, whatever is happening, whatever is affecting the creep meters, is not uniformly affecting the entire fault, because these creep meters are in different places. So each place may have some individual time history. And that's actually very typical and perhaps even expected from this transient behavior. If it was all uniformly sliding at a constant rate, then you would expect more or less the same. But this time dependence means that the slip is evolving as a function of space and time in different places at different rates.
Excuse me, any idea about the green line 3 years regression?
So that's a good question. Roger Billum thinks that this is real. He thinks that fault actually did reverse the sense of slip and went left lateral during this period. Because we do not know, we do not have any independent data to confirm whether this did or did not happen, I guess I'm a little bit skeptical. There could be perhaps some instrumental problems, but this is very, very intriguing. Yeah. So synthetic aperture radar is a space geodetic technique that involves a moving platform, for example, a radar mounted on an orbiting spacecraft. It sends pulses of microwaves down to Earth and then records whatever is coming back, the backscatter. As the satellite repeats the tracks, one can combine the data collected on the two subsequent passes or any passes that satisfy interferometric conditions. And one can form these so-called radar interferograms that tell you the amount of displacement that happened between points on the ground and the imaging instrument. This picture on the left shows the co-seismic interferogram from that El Mayor Cucapa earthquake that I mentioned just minutes ago. It involved several meters of slip on an earthquake fault that had roughly 100 kilometers length extent. So with InSAR, we are able to measure not only these large co-seismic displacements on the order of meters, we can also measure much smaller displacements on the order of millimeters that happen in the interseismic period. That's a picture from the ENVISAT covering the time period of 2004-2010 that I was showing you before. And these are recent Sentinel-1 measurements over the time period of 2016-2017 and 2017 to 2018. So same time period, just 2 different years. And you can see that in this time period, indeed, there was very little, if any, surface creep on the San Andreas. So that's actually in agreement with what the creep meters were showing. But then creep has resumed, and actually quite a bit of a creep has happened in the following year. This transition from almost no slip to rapid slip or significant slip did not happen gradually. Because of the creep meter measurements, we know exactly when it happened. These are, again, measurements from a number of creep meters that show that rapid slip or accelerated slip started on September 8th of 2017. And then it occurred for multiple months and involved a number of subsequent sub-events with the total amplitude of several millimeters up to a centimeter if we count up until now. This is an interesting time because on that day, on that hour, and almost to the minute, there was a large magnitude 8.2 earthquake that happened in Mexico, the south of Mexico, 3,000 kilometers away. So if you count, if you allow for surface waves to travel from this earthquake to our site of interest, slip on the fault started within minutes from the passing of these surface waves. So this is suggestive of dynamic triggering. If so, this would be very surprising, because you can imagine that from an earthquake that happened that far, the stress perturbations from the seismic waves that travel by would be very, very, very small. Right? So we went ahead and estimated what are the magnitudes of such stress perturbations associated with the traveling surface waves. We have several broadband seismic instruments located along the fault traces shown here. Turns out that the seismic records from these instruments are very similar, so we simply align them on the same arrival, took an average, and rotated the three components that each seismic instrument has, the north, the east, and the vertical, actually just the north and the east, into the fold parallel and the fold perpendicular. They're shown here. Out of these, we can compute strain components, or strain rate components. And then by multiplying these strain rates by whatever elastic modulus we think is appropriate for the shallow crust, we can come up with stresses. So stresses, dynamic stresses associated with seismic shaking. And then we can combine the normal stress and the shear stress into this so-called Coulomb stress, which is shown here. So that's the time dependence of the Coulomb stress, which we think is relevant to the triggering of that slow slip event. By looking at the magnitudes, so here's the scale of 50 kilopascals, you see that they are quite small. These are kinds of stresses that you put in the tire of your bicycle. These are also stresses that are comparable to tidal stresses. So the Earth is responding to the gravitational pull of the sun and the moon, and this kind of deformation is happening every day, twice a day, just from the gravity. Now I'm going to say a bit more about how we process the data and what kind of results we extracted from the InSAR data sets. As I mentioned, we are looking at this newer Sentinel-1 system that now consists of 2 satellites that are flying in the constellation. Typically, radar interferograms may look something like this. This is actually already a derived product. These are average displacements that happen over a certain period of time. And what the radar is measuring is the so-called line-of-sight displacement. So that's a distance, that's a projection of the total displacement vector onto the direction to which the satellite is sending waves, sending electromagnetic signals to the ground. So it's not a 3-component vector, it's a projection of that 3-component vector on the satellite line of sight. And we have 2 different viewing directions, 2 lines of sight that correspond to 2 orbits. So one is the descending orbit. This is when the satellite is flying from the north to the south. And the other is the ascending orbit. That's when the satellite is flying from the south to the north. The satellite is actually following the same orbit all the time. It's just the Earth that's rotating below it. And so there are times when the satellite goes up, and there are times when the satellite goes down, up in sky over the same area. So this is the line of sight displacement from, I think, the descending orbit. This is a line of sight displacement from the ascending orbit. And the way to look at these colors is just to realize that whenever you see a signal which has the same sign in 2 different lines of sight, it's dominated by the vertical motion. That's because the 2 lines of sight have the same sensitivity to the vertical motion. If you have a signal which looks consistent but has the opposite sign, it has to be the horizontal component. It has to be horizontal displacement, because the horizontal displacement has the opposite projections onto these different lines of sight. So we can take this one step further and just assume that displacements perpendicular to the fault are negligible. So all of the motion is happening either in the vertical direction or in the fold parallel direction. So under this assumption, we have 2 unknowns, the horizontal fold parallel displacement and the vertical displacement. And we have 2 observables that are coming from the ascending and descending line of sight. And so after doing this decomposition, essentially for every pixel, we would solve the system of equations, and we would recover the fold parallel displacements and the vertical displacement components. And this kind of a decomposition is useful because you can see that much of this signal is going into the vertical displacements. And the reason why these large vertical displacements are happening there is because of hydrology. So migration of water in the shallow subsurface may cause significant vertical motion, either subsidence or uplift, and this is what you see around here. The reason why we have these large vertical displacements there, even though this is a desert, is because of a canal that brings the Colorado River water up here to Los Angeles. And so it's probably leaking of the canal or some changes in the hydrologic conditions related to the water transport that is causing these large vertical motions. You can also see there is lots of hydrology here in the agricultural areas in the Coachella Valley. Now, the signal that remains in the horizontal component is much cleaner, and this is nice because that's the kind of a signal that we attribute to shallow creep on the fault, and we're able to model, we're able to explain it in some fashion. So as I said, we have these displacements at every given pixel of the radar image, and we have the full time series. This is the picture taken from the field. You can see the surface offset. There is this localized crack and a bit of an opening happening. That's from the same episode, from the same slip event that I was talking about. And at this location, we have about 1 centimeter of displacement measured in the field. With InSAR, we're able to measure displacements that are, in fact, even a small fraction of that. So we can push down the accuracy to a level of a couple of millimeters. This takes extensive processing, but this is possible. And on the right, we have the time series of displacements at different points along the fault. So these are different labels here that correspond to these particular locations. Horizontal displacements, vertical displacements. And the vertical dashed line corresponds to the timing of the Chiapas earthquake. And so you can see that at the time of the Chiapas earthquake, slip has accelerated significantly, and there is good evidence here that, in fact, we are, in fact, seeing this, the onset of dynamically triggered slip from the surface waves. When we compare the data obtained from different measurement techniques, so here the black dots are measurements from InSAR. If you just difference the displacements on both sides of the fault on this color map, plot them here as a function of distance along the fault, you can compare them to the geological measurements of offsets that are shown here by white triangles. And you can also compare them to the measurements of creep meters that were active at that same time. You can see that by and large they are within the measurement errors of each technique, but in some places we see also some systematic disagreement. So remember, in places where we have a good agreement between very local field measurements and much broader InSAR measurements, it means the deformation has to be extremely localized, so all the action is happening on that very narrow crack. In places where local measurements are underestimating what the InSAR data are telling us, it means that it has to be happening over broadly distributed deformation. So these types of observations motivated modeling efforts. And the kind of questions we're interested in include what mechanisms control this episodic behavior? Why does this shallow part of the fault decides to creep in episodes as opposed to just stable sliding? How these slip events be triggered by apparently very small dynamic stress perturbations, such as those associated with distant earthquakes. Can these fault sections in the shallow crust that produce unstable slip can also be a barrier to the co-seismic slip, as we saw in case of the Superstition Hills, for example? And what lithological conditions are required to produce such behavior, such unstable creep? So this last question was raised by a recent study by Wei, Kaneko, and others, who suggested that this type of a behavior, and these are data from the Superstition Hills fault, may be explained if one postulates the existence of a thin velocity weakening layer embedded in this shallow velocity strengthening layer. So this is kind of a sandwich structure. And the thickness of this layer has to be small compared to what is known as critical nucleation length. So that's basically the smallest size that is able to sustain accelerated slip. Turns out that if this velocity weakening layer is small enough, then it can start slipping faster. But once the slip propagates outside of this layer, it will be blocked. It will be stopped by velocity strengthening material outside. This requires rather special lithological conditions, because you can imagine that the existence of such a layer may be questionable even along a single fault, let alone in different locations around the world in which we see these kinds of behaviors. So we started exploring other types of models that do not require such special lithological conditions. And one class of models simply assumes that the variations in the parameter, stability parameter A minus B is monotonic in the shallow layer. So in these models, we simply fix the slip rates that are shown here in black and solve for the dynamic system in the shallow section that are shown in blue. And one question that we're interested in particular is how such a system be perturbed by very small external changes in stress. So to start with, we consider the so-called reference model, in which we have an linear increase in the effective normal stress with depth. The distribution in the A minus B parameter is shown here. These two combined result in the nucleation size that is a decreasing function of depth. And the model parameters were actually chosen a little bit by trial and error to reproduce features that we observe on the Southern San Andreas. So this diagram shows the logarithm of the slip rate as a function of depth. So here we're at the surface. This is the bottom of the sedimentary layer that hosts these slip instabilities. And you can see that slip accelerates roughly every 2 years. This is somewhat similar to the kind of behavior that we observe on the fault. We can then take that background model and perturb it by quasi-periodic stress change. And we just use a model that mimics quite closely the stresses that are associated with the passage of surface waves. And these diagrams on top correspond to a case of a single, rather weak perturbation. So this happens at that particular time. And you can see that at the time of the perturbation, it's able to accelerate slip and result in a slightly larger step in the displacement. But then it also delays the occurrence of the next cycle. And this is a blow up of what is happening here at a very short time scale. You see as this wave train passes by. At the time when the Coulomb stress changes are largest, you have the largest rates of slip. So slip kind of goes in this periodic pulsing sequence and then goes back to the steady state. And then this last simulation here corresponds to the case of two perturbations. So we start with one perturbation here around year 11, which is followed 7 years later by another perturbation, a weaker perturbation, around year 17. So this is again roughly taken to represent the perturbation from the El Mayor earthquake and the Chiapas earthquake that were separated by 7 years. These are the same records, just displayed in terms of the slip history as a function of time at different depth slices. This one is at the surface, the red curve. The brown curve is at depths of 1 kilometer, and the black curve is at depths of 2 kilometers. And you can see that in case of perturbation, the system evolves into this semi-periodic behavior where we have events that are happening roughly a couple of years. They have amplitude of maybe a couple millimeters, several millimeters, similar to what is happening on the creep meter records. And if we perturb this with a single weak perturbation, you can see that it sort of accelerates a little bit and then maybe delayed somewhat. And then this is the perturbation that we think is appropriate for the history of slip events on the San Andreas. And you can see that indeed this is very similar to what the creep meter records suggest. So here we have a large instantaneously produced triggered slip, then virtually no creep rate over the period of subsequent 7 years. And then at the time when the second perturbation comes in, we have another slip event, and it eventually, after all that memory is erased by constant tectonic loading, it returns to this original state.
Can I ask you to go back by one slide?
Sure.
Okay, here. Now, the typical tuning of a surface wave train that is injecting this dynamic perturbation, it's transient, could be varying in amplitude and period.
Yes.
According to the source.
Yes.
Have you tried to play with different periods and different amplitudes to see if this resonance can occur in different conditions?
Yes, I don't think there is any resonance phenomena here, but the period and the amplitude of this trial perturbation, yeah.
Double excitation is giving something, right?
Yeah, so this periodic source was basically chosen to reproduce quite closely to what the seismometers were showing. So they have the right period for the seismic waves from an earthquake of a given epicentral distance, and they also had the same amplitude as recorded by the seismic instrument.
To change the location of the source, amplitude and the period that you're going to get at the site will be different.
Certainly, yeah. For different events, different radiation patterns, different size of earthquakes, the frequency content would be different, the amplitudes would be different.
Did you try to play with these parameters with different?
We did not go through the exhaustive search for what will trigger a slip event versus what would not trigger, just because we had an observation that we were looking for a single model that is just able to explain what is happening.
Right?
Yes, yes. But having said that, indeed, it's very, very well known that, for example, in case of triggered micro-earthquakes, so not slow slip events, but triggered micro-earthquakes, the frequency content is very, very important because for the same seismic wave, triggering is usually associated with the passage of S waves. In other words, the micro-earthquakes will be triggered by the surface waves, but not by the P and S wave. So the main difference is the amplitude and the period. And so there is some threshold that is frequency dependent and the amplitude dependent. Yeah, that's a good point. All right, so I think I need to speed up a little bit. Let me skip this part and just kind of summarize what we inferred based on our observations. In case of a fault that has this shallow creeping zone, several things are happening. So first of all, this creeping area, of course, releases stresses that would otherwise accumulate here interseismically, which means that the total area of the fault available for the earthquake when the large earthquake happens would be smaller. This would reduce the seismic moment, and that's good news for seismic hazard. On the other hand, by relieving stresses in this shallow portion, we are increasing stressing rates on the deeper lock portion of the fault, right? So if you are kind of breaking the rope and some of the fibers are failing, it means that you're putting more load on the remaining fibers. And this means that the timing of the next event is advanced. So it has this sort of double effect in terms of the advance of the next earthquake. By allowing or by having this shallow creep process, which is time dependent, we also perturb the likelihood of the occurrence of large events, because if you imagine that if you load something very slowly at the constant rate, the likelihood of triggering something big would not be the same as something that happens episodically. So every time you have accelerated creep during these slow slip events, it is perturbing stresses in a time-dependent fashion on the deeper portion of the fault that is locked and we think is ready to go. And so these accelerated events must have some triggering potential. So just to conclude, we see that shallow fault creep can show quite a rich behavior. So this can include quasi-steady creep, as observed in some faults. It can include triggered events, for instance, due to passage of seismic waves from distant earthquakes, and it can also include spontaneous slow slip events. I showed data that revealed details of a slow slip event that occurred on the Southern San Andreas starting in September of 2017. The timing of this event to the minute suggests that it was triggered by dynamic stress changes from a Chiapas earthquake. I also showed data suggesting that the widths of the surface shear zone, presumably representing distributed shallow creep, can in fact evolve as a function of time. At some point it can become narrower, at some point it can become wider. And finally, the models that we considered, at least we have a set of models that are able to reproduce a set of puzzling observations, including the triggering thresholds, the amount of the triggered response, so the amplitude of the triggered slip, and also the sequence of several triggering events that correspond to different earthquakes. So for those of you who are interested in details, I think the link was sent around for the paper. We just had a paper that came out recently in JGR, so I encourage you to take a look at that. So thank you very much, and I will answer questions.
Thank you very much for this very interesting talk. Are there any questions?
Yes.
Yes, please.
So you showed this is a shallow fault creep, right?
Yes.
But I mean, in this region, are there any low frequency earthquakes or repeaters? I mean, how do you say that this is really just the shallow layer that's
goes into the slow sleep and not something closer to the base, seismogenic zone?
Yeah, so it's very easy to document the shallow creep because we see a discontinuity right at the surface. So there's no ambiguity whether slip is happening across the fault trace or not. This is what is directly measured. Now the depth extent is controlled by the behavior of the displacement as a function of distance away from the fault. Because we have measurements not only on the fault, but also as a function of distance from the fault, we can invert these data and say how deep that shallow creep extends. Turns out that the answer is about a couple of kilometers, and this correlates really well with the thickness of the sedimentary layer. So I think data are consistent with the story that it's the sedimentary layer that is hosting slow slip as well as the quasi-steady creep. And then crystalline rocks in the basement are seismogenic. So, but this question about repeaters, there is not much of a seismicity happening on the shallow crust. And I do not think seismologists were able to find many repeating earthquakes on San Andreas except around Parkfield. So
yeah, the Parkfield area is full of low frequency earthquakes.
Yeah. Parkfield is different because in Parkfield you have a transition to a fault which is fully creeping all the way from the top to the bottom. There is really, well, Parkfield itself actually is very similar to here because in Parkfield we have shallow creep and then locked section and then a deeper section, but it's on the boundary with this transition to the fully creep section. So the reason why we have repeating earthquakes is that you have to have these kind of patches of velocity weakening crust, which are surrounded by this larger area that is stably sliding, is able to lock these patches. So kind of they're being dragged by the fault around them, and that's not what is happening on the Southern San Andreas.
Is there another question? Yes.
Okay, this beautiful dynamic picture can be mapped also in different kinematic conditions in that part that can be used to model hazard scenarios.
Yes.
And this has a dramatic impact on this. Has someone, maybe in SCAC, tried to implement these kinematic visions and to produce different ground shaking scenarios here? Because everything is going, visions will be totally different.
Right, so there is a large effort to try to relate what the science is telling us to the possible societal impact. So we know that there is a potential for magnitude 7 plus 7.7, 7.8. We know where it's going to happen. We know roughly what size of the earthquake this will produce. And then the question is what kind of impact it will have on the built infrastructure, what can we expect in terms of society response and things like that. And there's a large effort called CyberShake and TerraShake, basically doing exactly that. So these are deterministic models that are informed by the best available science, and they kind of explore what are the consequences of this kind of event.
Dynamics here really can lead to different kinematic rupture models.
Yes.
Totally
Yeah.
different.
Yeah. And so the way this is handled in these calculations is that there is some stochastic distribution of parameters. We don't know everything, right? And so just a number of solutions, and then one can sample these solutions in some
This dynamic
Bayesian way.
vision could, design some frames in this stochastic tradition. You can guide them in some way.
That's right.
Because dynamics.
Yeah. So this is already happening, but yeah.
Okay.
Is there some other curiosity? Maybe from part of the students. We have many students who will be shy. Maybe.
Everything was either very clear or very unclear.
Okay, so if there's no other question, I think we
I
can
have
close.
one last question.
Okay.
Number 3, you suggest that the 8.2 Chiapas earthquake could provide this dynamic stress, but that doesn't make sense. When the Cucapa earthquake is much closer, the stress induced by that magnitude 7.5 Mayor Cucapa earthquake would have been much higher. So why didn't it generate the triggering rather than Mexico?
The Cucapa earthquake, in fact, did produce a large triggered event. So remember, the creep meter measurements show about a centimeter of triggered slip that happened instantaneously at the time of the Cucapa earthquake. And then creep meters were shut down. not much creep was happening 7 years after the El Mayor, and then the Chiapas basically kicked it into the high gear and it started accelerate creep again. So, yeah. It is surprising that, however, that in terms of the order of magnitude, the contribution or the impact of the El Mayor Cucapa was maybe 100, maybe 1,000 times larger, and yet the total magnitude of the response was not 1,000 times different.
Yeah, yeah.
So that just indicates that the system is highly nonlinear.
I had a small question. We were looking here for hydrologic induced stresses. What about hydrologic induced stresses at the San Andreas Fault? Could that give you some induced creep?
This is something that we have not looked into closely. I'm pretty sure that, well, there are reasons to expect that hydrology would be coupled with the fault behavior, and that is because if you have a system with saturated pore fluids in the pore space, whenever you have changes in the pore pressure, this will couple into the effective normal stress. So by increasing the pore fluid pressure, you will reduce the effective normal stress, and that, of course, either brings the fault closer or away from the failure. So there are very good physical reasons to believe that hydrology would affect things. We don't have a good way of saying exactly what the subsurface hydrology is doing. Perhaps measurements in boreholes would be one way of doing that. There is another interesting relationship to hydrology that I did not mention. You remember that much of Southern San Andreas is right next to the Salton Sea. There is a big salt lake that was formed by the Colorado River when it started flooding this area. And geologists are pretty convinced that large earthquakes on this part of the fault were happening when the lake level was high. And so right now the lake level is about several tens of meters lower than it used to be during the last high stand, and perhaps this is related to the fact that we have this extended period of no seismic activity. So if that's the case, I guess our solution for delaying the earthquake would be to drain Salton Sea and let fluids out.
Okay, I think some of the students have other lectures, so I think we have to close this session, but I think you are here still for some time.
Yes.
For answering private questions. So thank you very much to everybody who has attended. And for the next